I'm going to have one lecture on eigenvalues and eigenvectors, and then we're going to apply that in the next section to differential equations. Eigenvalues and eigenvectors is quite an important topic, well beyond just this one application, and I really should be spending a week on it, but I simply don't have the time. So remember, if A is a matrix and V is a vector, we say that V is a lambda eigenvector if A applied to V is lambda times V. And so that is that when you apply this matrix to this vector, you get a multiple of the vector. And lambda, which is a scalar, is the eigenvalue. And the vector itself is the eigenvector. And we last time we established a couple of basic facts. So the one is that lambda is an eigenvalue if and only if the determinant of A minus lambda times the identity is equal to 0. So that's an important equation. So you should view this as an equation for lambda. And second of all, if you fix if lambda is an eigenvalue, yes, if lambda is an eigenvalue, then the lambda eigenspace is the set of lambda eigenvectors, and this is a subspace of the vector space. And okay, so both of these things I talked about last time, and I'm going to talk about them a little more in a little bit more detail. Okay, here's a really basic example, and in some sense I recommend that you think of all examples are more or less like this. So let's take A to be the following matrix. Let's suppose it has some 4s and say 3 and a couple of 2s and 3 1s, and it's diagonal. So what are the eigenvalues? Well, if you apply our test, A minus lambda I is 4 minus lambda down to 1 minus lambda, and the determinant of it is 4 minus lambda cubed times 3 minus lambda times 2 minus lambda cubed times 1 minus lambda. And it's obvious that if you set that equal to 0, the solutions are 4, 3, 2, and 1. So that is to say, the eigenvalues are the diagonal entries. So that's a basic fact. If A is diagonal, the eigenvalues are the diagonal entries. And secondly, if lambda is an eigenvalue, I'll always write V sub lambda for the corresponding lambda eigenspace. What's its dimension? The dimension of V sub lambda is what? Well, for example, if you take the 4, if you take lambda is equal to 4, what's the dimension of the space of 4 eigenvectors? Well, if you think about it, and I'll show you in a second, it's 3. It's the number of times lambda occurs. So in this example, what I recommend you do is you think of this as breaking this up into blocks, like this. And the sizes of these blocks are 3, 1, 3, and 3. And this block up here, whoops, I shouldn't have done that. This block up here corresponds to the 4 eigenspace. What is the 4 eigenspace? Well, it's the following vectors. It's vectors which have anything in the first 3 coordinates, and all the remaining coordinates are 0. And similarly, V3 is just this coordinate, which is to say 0, 0, 0, x. And V2 is 4 zeros, x, y, z, and 3 zeros. And finally, V1 is 7 zeros, followed by anything x, y, z. And so the dimensions of these spaces are 3, 1, 3, and 3. Okay, so that is sort of the prototypical example. When a matrix is diagonal, it's very easy to figure out what its eigenvalues and eigenvectors are. So the conclusion of what I just said is that diagonal matrices are extremely easy to understand in terms of their eigenvalues and eigenvectors. And let me illustrate that not all matrices are quite that easy. So I'm going to do 2 examples. I'm going to do A is equal to the diagonal matrix 2, 0, 0, 2. And I'm going to do B is the matrix 2, 1, 0, 2. So this is diagonal, so we totally understand it. The only eigenvalue is 2, and the 2 eigenspace is the whole vector space, which is to say every vector is a 2 eigenvector. And another way to say that is that V2 is the kernel of A minus 2 times I, and that's the kernel of, well, A minus 2 times I is the 0 matrix, and so of course that's everything. That's all of our 2. Now this matrix is similar, except it has this 1 here. So what are the eigenvalues of this matrix? Well, to calculate the eigenvalues, you subtract lambda from the diagonal, and you take the determinant, and it's an upper triangular matrix, so the determinant is just 2 minus lambda squared. The 1 doesn't matter, it's the product of the diagonal fellows. And the only solution to this is lambda is equal to 2. And so you look at these two 2's and you say, well, I think that the dimension of the 2 eigenspace is 2. But you'd be wrong. This 1 messes you up. So let's calculate what is V2, the 2 eigenspace. Well, that's the kernel of 2 minus 2, 2 minus 2. Right? You plug in lambda is equal to 2 here, and you calculate the kernel, which is to say the kernel of 0, 1, 0, 0. And that's not 0, so the kernel is not two-dimensional. What is the kernel of this matrix? Well, this matrix sends xy to y, 0. And so the kernel is exactly the vectors where y is equal to 0. So that is to say x is anything and y is 0. So in other words, this is all multiples of the single vector 1, 0. And it's one-dimensional. Okay, so this is an example. If the matrix isn't diagonal, it's possible that the sum of the dimensions of the eigenspaces doesn't add up to n. If it was diagonal, it added up to n, but if it's not diagonal, it could be smaller. The eigenvalues are still these 2's, the diagonal entries, but so maybe I should say that here. The eigenvalues are the diagonal entries, but the dimension of the corresponding V lambda could be less than the number of lambdas on the diagonal. Here there were 2 lambdas on the diagonal, and the dimension of this vector space was 2. Here there are 2 lambdas on the diagonal, but here the dimension is only 1. Okay, I'd like to pose a question now. Suppose A is an n by n matrix. Does it have at least one eigenvector and eigenvalue? So I'd suggest that you pause and think about that for a minute, trying to decide whether this is true. And when you've thought about that for a second, come back and I'll tell you what I think. All right. What do you think? Well, I was a little I was a little bit vague about what kind of matrix A is. A could be real, and we could be talking about Rn, or A could be a complex matrix, and we could be talking about Cn. And if A was real, the answer is no. And we saw an example last time where you take A to be 0, 1, minus 1, 0, because the equation that you get, A minus lambda I, is lambda squared plus 1, and that's never equal to 0. On the other hand, if it's a complex matrix, it turns out the answer is yes, and that's quite an important fact, and it's not at all obvious. This no, I hope you, at least some of you, thought of this example to see that the answer is no. But the fact that if for a complex matrix the answer is always yes is quite a non-trivial fact. So why is that? So suppose A is an n by n complex matrix. Then we look at, well, I'll give this thing a definition. The characteristic polynomial of A is this matrix, is this determinant A minus lambda times the identity. So it's this thing that we mentioned when that you use when you're computing eigenvalues, and this is a polynomial in lambda. What does this look like? If you expand it in terms of lambda, it has the leading term is minus 1 to the n lambda to the n plus cn minus 1 lambda to the n minus 1 plus some c0. That's the characteristic polynomial and let me put the last two terms, C1 lambda plus C0. It's a polynomial in lambda of degree n. It's a polynomial in lambda of degree equal to n. So let's look at that a little more closely. Okay, so I'm going to write char A for the characteristic polynomial of A. And that is to say, it's this determinant of A minus lambda I. And another bit of terminology, the characteristic equation of A, that's an equation. And the equation is, you set this thing equal to 0. Determinant of A minus lambda I is equal to 0. And as I said before, if A is an n by n matrix, it's A11 down to A n n, and so on. And let me write A minus lambda I here. You subtract lambda from all of these diagonal entries, and there's a bunch of other entries. And if you take the determinant of this, what do you get? Well, you multiply all these terms in various ways. One of the terms that you get is the product of all of the diagonal terms, and that has a minus lambda to the n in it from each of these minus lambda terms. And then all of the other terms involve products of lambdas, but lower order. Lower order in lambda. Lambda to the n minus 1 and lambda to the n minus 2 and so on. So that's what I mean by saying it's a polynomial of degree n. Okay, so let's go back to our question. You have this A, and I want to know whether it has an eigenvalue. Well, that's exactly the same thing as asking, does the equation determinant of A minus lambda I equal 0 have a solution? Well, this is more or less an arbitrary polynomial of degree n. So the question becomes, suppose I take a polynomial a0 plus a1 lambda plus dot 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 an lambda to the n and set that equal to 0. Does this have a solution? Okay, so why am I saying this? Well, this is a polynomial of degree n. And so it's more or less the same thing to ask if any polynomial of degree n has a solution. Now, this polynomial happens to have this minus 1. The leading term is minus 1 to the n times lambda to the n, but it doesn't really matter. You can just write an arbitrary polynomial here. Does this have a solution? So, well, let me put a box around. Let me highlight this. This is the question. The AIs are complex numbers, and I want to know whether this polynomial has a solution. And if it does, then every complex matrix will have at least one eigenvalue. So, well, I'm going to ask you to pause again. The question is, if you take an arbitrary polynomial of degree n with complex coefficients, does it have a complex solution? So, for example, lambda squared plus 1. Does that have a solution? Well, if I was talking about real numbers, it wouldn't, but for complex numbers, the answer is yes. Lambda is equal to plus or minus I. So there's a hope for complex numbers. There's certainly no hope for the real numbers. But if I allow complex numbers, this is possible. So why don't you pause and think about that for a moment, and we'll come back and say what's true. Well, here's the answer. This is an extremely important fact. This is called the fundamental theorem of algebra. So just by its name, it's obviously important. It's fundamental, and it's the fundamental theorem of all of algebra. And what it says is the following. Suppose I have a polynomial f of z is a0 plus a1z plus a n z to the n, where the a's are complex. And I'm using z here. When you're talking about complex numbers, it's sort of more common. You can think of z as being x if you want. Take a polynomial of degree n, polynomial of degree n. Then the conclusion is, I'll write it in two ways. The first one is that this has at least one root. I'll call it r in complex numbers, such that f of r is equal to 0. So, in other words, to say a root means that it's a solution to f of z is equal to 0. And another way to say the same thing is that this has n roots, r1 up to rn, which satisfies f of ri is equal to 0. In order to make sense of that, the n is counted with multiplicity. So it could have n distinct roots, or it could have one root counted n times, or anything in between. For us, the main thing is this right here. It has at least one root. And so an immediate consequence of that is that if A is an n by n matrix, it has at least one eigenvector and eigenvalue. Well, I should really say at least one eigenvalue with its corresponding eigenspace. It has at least one eigenvalue. And the reason is because you just take the equation determinant of a minus lambda I is equal to 0. This is a polynomial of degree n, and by the fundamental theorem of algebra, it has a root. It has a solution, lambda, and by what we've talked about, this lambda is an eigenvalue. All right, well, let's do the standard example. Let's take A to be this matrix 0, 1, minus 1, 0, this complex matrix. What do I mean complex matrix? This is a real matrix. Well, real numbers are complex numbers. Think of it as a complex matrix. Does it have any eigenvalues and eigenvectors? Well, the characteristic polynomial of A is lambda squared plus 1. And I'm trying to solve that is equal to 0. And sure, that has two solutions, I and minus I. So that illustrates why you need the complex numbers here, of course. If this was over R, the answer would be no eigenvalues, but if you're thinking of this as a complex matrix, it has in fact two eigenvalues, I and minus I. All right, now there's a basic fact which is easy to see, which is you have your matrix A, and suppose you have a bunch of eigenvalues, lambda 1 through lambda r. They're distinct eigenvalues, so lambda I is not equal to lambda j. And suppose I have corresponding eigenvectors v1 through vr, where vi is a lambda I eigenvector. Then the conclusion is that V1 through VR are linearly independent. Okay, so I'm just, because of time, I'm not going to prove that. It's lemma 8.13. And so there's an important consequence of that. So I'll state two versions of it. The first one is, suppose A is an n by n real matrix. If it has n distinct eigenvalues, then, well, let me write them as lambda 1 through lambda n with the corresponding eigenvectors v1 through vn, then v1 through vn are a basis of Rn. So this is extremely nice. If you have an n by n real matrix with distinct eigenvalues, you can find a basis which is well suited to the matrix. Of course, when you have a matrix, if you have an n by n matrix, there are many, many different choices. There's the standard basis or many other choices. There's a particular choice of basis which is extremely convenient if you're working with the matrix A, and that is to say it's given by these vectors with distinct eigenvalues. And the similar thing happens over C. If A is n by n complex, and it has distinct... I'm sorry. I forgot an important word here. These eigenvalues have to be real. Whereas if you have an n by n complex matrix with distinct eigenvalues, and similarly, I'll label them 1 through n with corresponding eigenvectors v1 through vn, then v1 through vn is a basis of Cn. So these two statements are essentially the same, with the crucial addition of this word real. If you have a real matrix, it could have n distinct eigenvalues. If some of them are complex, then you lose. But if it has n distinct real eigenvalues, then you can get a basis of Rn this way. And similarly, if you have an n by n complex matrix, it just has to have distinct eigenvalues. It doesn't matter where they are. As long as it has n distinct eigenvalues, you can take the corresponding eigenvectors and get a basis of Cn. Okay, so why am I making such a big deal out of this business about distinct eigenvalues? So let's just do the complex case. Suppose A is complex, n by n, and it has eigenvalues lambda 1 through lambda n, and they're distinct. And the corresponding eigenvectors are v1 through vn. So A is a complex n by n matrix. So it's a map from Cn to Cn. And it's the map, it's the map of a linear transformation from Cn to Cn using the standard basis. That's what it means. And, well, question, what is the matrix of A in this new basis? So the standard basis here, let me just remind you, is of course E1 through En, where EI is 1 in the ith spot and 0 everywhere else. Well, when you have a linear transformation, you can use whatever basis you want. So it's my prerogative. I'd like to ask you what to use this basis, V1 through Vn. And what is the matrix? Well, A V1 is, by definition, lambda 1 V1. And so that says that with respect to this basis, AV1 is equal to lambda 1 V1 and nothing in the other columns. And similarly, AV2 is equal to lambda 2 V2 and so on. It's diagonal with these diagonal entries, with these lambdas down the diagonal. So one way to say this is we say that A is diagonalizable. So way back at the beginning, I was saying that diagonal matrices are the nicest, and well, a matrix doesn't have to be diagonal to be nice as long as it's diagonalizable. It's nice because then if you just choose the appropriate basis, you can make it diagonal. And well, that's something that we do a lot. If you're given an arbitrary matrix, its behavior with respect to the usual basis could be very complicated, but for what you want to do for solving a problem, it might very well be much, much easier if you choose this special basis, which is suited to A, which makes A diagonal, and then it's very easy to compute with. Okay, so that's a good place to stop. I will see you in class.